Have you ever stopped and wondered about the little bit of magic that's inside so many of our gadgets? You know, from a kid's toy to an electric fan, they've all got this tiny engine that somehow turns electricity into motion. Well, in this explainer, we're going to pull back the curtain on that incredible everyday science behind the electric motor.
I mean, seriously, just take a look around your house. Electric motors are absolutely everywhere. Your electric toothbrush, your hairdryer, that fan cooling you down, they all share the exact same fundamental technology that we're about to break down.
It really does feel like magic, doesn't it? You flip a switch, electricity starts flowing, and poof, something starts to spin. So what's really going on here? How does pure electricity get turned into physical spinning force? That's the exact mystery we're about to solve.
Okay, let's dive in. We're going to frame this as a piece of everyday magic. And I promise, it might seem complicated at first, but by the end of this, you'll see exactly how the trick is done.
But, you know, before any great magic trick, you've got to understand the props. And for us, that means getting a handle on the two key ingredients, electricity and magnetism. Let's just cover the absolute basics we need.
First up, the electric circuit. The easiest way to think about this is like a racetrack for electricity. As long as the track is a complete loop, the electricity just keeps on flowing. But the second you create a break in that path, like opening a switch, everything grinds to a halt. The path has to be complete. All right, our second ingredient is a permanent magnet. I'm sure you've played with these. It's got a north pole and a south pole, and its magnetic field is just, well, it's always on. You can't flip a switch to turn it off, it's just permanently, well, magnetic.
And how these magnets work all boils down to one simple, unbreakable rule that you probably learned as a kid. Opposite poles attract. North can't help but pull towards south. But identical poles, they repel. They push each other away. This fundamental push and pull, that's the force we're going to harness.
Okay, so we've got our circuit and our permanent magnet. Now for the really cool part. Let's combine these ideas to create something totally new, a magnet that we can actually control.
And you know what? It's surprisingly easy to build one. You just take a regular metal bolt, not a magnet at all by itself, then you wrap it in a bunch of wire. And finally, you connect that wire to a battery, completing the circuit. The second that electricity flows through the coil, boom, that bolt becomes a temporary magnet.
And this right here reveals the superpower of an electromagnet. Unlike a permanent magnet that's stuck being on, we can turn this one on and off just by controlling the electricity. But here's the real game changer, we can reverse its poles.
And this is the absolute key to everything. If we just flip the battery around and make the current flow in the opposite direction, the north and south poles of our electromagnet instantly swap places. This ability to flip the polarity on a dime, that is the secret ingredient for making something spin.
All right, we have all our pieces on the board. It's time to put them together and finally unlock the secret to creating continuous, non-stop rotation. So picture this. We place our new electromagnet on an axle, right between two permanent magnets. The moment we turn it on, what's going to happen? Well, that rule of magnetism takes over. The north pole of our electromagnet gets pushed away by the outer north pole and pulled towards the outer south pole. It's going to spin until it lines up perfectly.
But what if, at the exact moment it snaps into alignment, we instantly reverse the current and flip its poles? All of a sudden, its north is next to the outer north again. So what does it do? It gets pushed again, spinning another 180 degrees to try and realign. If we can keep timing that flip perfectly over and over, it will never stop spinning.
Now, to turn this simple idea into a more efficient motor, we're going to make a couple of upgrades. Instead of a clunky bolt, we'll use a loop of wire. This is called the armature. And instead of flat side magnets, we'll use stronger, curved magnets that wrap around the armature. This stationary part is called the stator.
So this is great in theory, but there's a huge problem. We can't have a person sitting there manually switching wires back and forth 1,000 times a minute. We need the motor to do this all by itself.
We know the secret is constantly switching the current's direction. That's what creates the endless push. But yeah, doing it by hand? That's obviously not a real solution.
So the big engineering question becomes, how can we design a system where the motor's own spinning motion automatically flips the electrical current for us?
Well, the answer is just an absolutely brilliant piece of engineering called the commutator. At its heart, it's a simple metal ring split in half with a couple of gaps, and it's attached directly to our spinning armature loop. So as the armature spins, the commutator spins right along with it.
Okay, let's break down this genius little device. We have two stationary contacts, called brushes, that are constantly feeding power.
As the armature spins, the commutator spins with it. And watch this. Each brush touches one half of the ring. But then, as it spins past the halfway point, it crosses that gap and makes contact with the other side of the ring. That simple physical switch is what reverses the flow of current through the loop, which flips the electromagnet's poles, which gives it another kick to keep it spinning. It is a perfect, automatic switch that's powered by the motor's own motion. So clever.
So now we have a real, working, self-sustaining motor, but we can make it a lot smoother and a whole lot more powerful. Let's see how. You see, a single loop of wire has a dead spot where it can kind of get stuck. The solution? Just add more loops, and we split the commutator into more segments to match. This makes sure that at any given moment, at least one of the loops is in the perfect position to get a strong magnetic push. This creates a really smooth, continuous spinning force, which we call torque. And of course, the more times we wrap the wire and the more electric we pump in, the stronger the electromagnets get, and the faster and more powerful the motor becomes.
So let's do a quick roll call of the final parts. We have the stator, those are the stationary magnets on the outside. We have the rotor, that's our spinning armature with all its wire loops in the middle. And that rotor is connected to the axle, the rod that actually sticks out of the motor and does the work like spinning a fan blade or a toothbrush head.